Hi everyone. If you can hear me, say yes. Great. Okay, how many people do we have today? Okay. Great. Okay, let's start. So the first thing I want to talk about is I already made a couple of changes on the web page. Someone suggested that we should have like a pointer for like an interesting reading or suggested reading for each topic on the lecture, for each lecture. So yeah, I think it is a good idea. It is a great idea. So I'm already did that. So as you can see on the lectures, you have another column called reading suggestion. And what I did is I put like a name for each book. So we have B1, B2, B3, right? And actually I'm added already a couple more books. So now we have 10 books, and you have access to those books on the UBC library, of course. Those are for free. So for each lecture, this is, for example, this is book 4, chapter 5.4, or book 3, chapter 7, right? So you can read something if you want. Again, these are suggestions, right? These are optional readings. It's a lot of content to read. If you want to read those, it's very good actually, and you will be in a better position in the lectures, of course, right? So it is good if you have time, but it's not required. Only there are some lectures in which we will require. So for example, in the case of ray tracing, the lectures for ray tracing, those are mandatory because you literally need to write your own ray tracer based on those books. But we will have time eventually to get into those lectures. Okay, what else? Okay, and for today, I have the PDF already. So please, I give you 1 minute or something like that to maybe download the PDF if you want to get the PDF and do your own annotations on that PDF. Because yeah, many people were asking. I'm not sure if I will be available to upload the PDFs like a day before or something, because I'm always making changes and depending on your questions on Piazza, I'm changing stuff on the PDF. So yeah, I usually trying to improve everything at the final moment. But yeah, I will try to upload everything. Okay, so let's start for today. We have a lot of stuff to talk today regarding the rendering pipeline. Okay. Good. And let me I need to minimize a couple of windows here because it's impressive teaching online the amount of floating windows we have. Is the theory assignment due to 25 or 23? It's on the webpage. I mean, I don't remember right now, but it's on the webpage. Yeah, the due date is on the webpage. I will try not to answer questions on the chat because I have a lot of content today, so I will just keep the pacing. So we have TAs on the session, so yeah, they will be able to answer your questions. We will have obviously time at the end to answer questions. Okay, so please say yes if you can see my screen with the Dragon and rendering pipeline 2. Perfect. Good. Okay, so these are the learning goals for today. Okay, so we will continue with the rendering pipeline. So we will talk a little bit more about the vertex shader, but like in deep. I will explain the vertex shader variables. This is very important for your intro assignment. I will explain what the interpolation means, right? We will not see the math yet, but we will see like what is that. We'll also see the concept of tessellation and the geometry shader, right? So those are the learning goals for today. Okay, so let's start. So we were saying that the rendering process is like a tiny factory, right? And there's a lot of data that we can send to that factory. And in the end, we need to obtain something, right? A 2D pixel image. So the data we need to send, we already talked about that on the previous lecture, right? So we have primitives, points, triangles, lines. those are the 3D objects, right? We also have coordinate frames. I mean, we haven't talked in deep about coordinate frames. That will be, I think that will be the lecture on Monday, I think. We also have materials, right? Colors or textures, information about the lights, the type of lights, the cameras, right? Obviously the coordinate frame of the camera. So we have a lot of information, right? And we need to take that information, get that information into this tiny factory that has different stages inside. And in the end, we have this beautiful car, right? So this is what we had last time, right? I think the last time we were talking about that, this is the slide we had. This is the OpenGL pipeline. We were talking that we have primitives and the info of the scene, right? And we just basically are following, right, the pipeline on this direction, right? Following the arrows. By the way, because I mean, nobody has asked this time, but I think someone asked on another course of mine, is the rows here. I mean, there isn't any like special meaning on the rows, right? I mean, this is just a layout I choose because I don't have enough space to put the pipeline like in a horizontal mode, right? Because it's just huge. Okay, so this is a better like square version of the pipeline, right? So we already know that we need to send data and geometry, right? That gets into the vertex data, and we follow everything. And at the very end, I need to add another stage, right? That is a per fragment operations. That stage is new, and that is the very last part of the pipeline. This stage is not usually, I mean, it's kind of like avoided in some books, but it's super important because it's the very last part. The actual pixel painting of the entire pipeline. Okay, so now let's take a step back a little bit because this is a very large pipeline, and let's take a look from like an upper level, okay, like a very conceptual level. So a very simplified version of the rendering pipeline should be something like this, like 4 main stages. So we have the application that happens usually on the CPU. When I say usually is because sometimes what you can do in the application is also processing data in the GPU, right? But in general, the application is running in CPU. So what is the CPU application stage? This is where you are defining all your geometry and scene, right? So it could be, for example, a game engine like Unity or UDK, or it could be Blender or Maya or 3 Studio Max or something like that, right? It could be, in the case, for example, of your assignment, your JavaScript is your application stage, right? So your JavaScript will not be processed on GPU, right? GPU are the shaders, right? So the JavaScript is somehow some parts of that. I mean, not everything on the JavaScript will be processed in the CPU, but some parts of your JavaScript is basically your application stage, right? Then there's the part of the GPU, what is entirely processed on the GPU. These sections: geometry processing, rasterization, and pixel processing. So let's see what those sections do. So basically, if I just get rid of the application stage, because that is like the outside part of the pipeline, we have the geometry processing. That is basically the one that is getting the data and processing the data. Obviously, when I'm saying data, I'm saying again primitives, vertices, textures, normals, a lot of information that we fit to the program. And this is obviously happens in 3D, right? Then the geometry processing, sends that data already computed, already processed, sends to the rasterization section or the rasterization stage. That section is also happens in 3D. And basically the goal of the rasterization is to define the fragments. And here is one of the most interesting concepts of computer graphics, the difference between fragments and pixels. Because the very last stage, the pixel processing, it is not in 3D anymore, it's already in 2D, and it's basically just painting pixels on your monitor, okay? So what is a fragment? A fragment is like a 3D projection of a pixel, okay? So let's see the next slide. So this is how it looks, kind of. So basically the the geometry processing section is processing the data, right? In this case, for example, it's processing this triangle, right? It sends information of that triangle to the rasterization section. When I say it sends, is because in geometry processing, everything is in 3D, right? But it needs to apply different transformation matrices to get the final position of that triangle in screen space, okay? So it goes to the rasterization part. It's already in screen space, but this screen space is not yet 2D because you have depth information. You have some information that is actually still 3D, okay? So the fragments, the way rasterization works is basically for each pixel on your image. So imagine that this frame here is your monitor, right? And every tiny square here represents a pixel, okay? So for each pixel, you need to identify in the rasterization section, you need to identify which part of this triangle correspond to each pixel. The part of the triangle that corresponds to a specific pixel, that is called a fragment, okay? So it's very similar indeed, right? It's very similar to a pixel, but it's not a pixel yet because a pixel is the final data that we output, okay? And pixels are unique. That is also super important, right? So once the image is created and we have an image on our monitor, right? For every pixel on your monitor, there's only one final pixel data that you process, right? However, fragments are not unique because for a single pixel here, for example, maybe there are fragments. There's this fragment from this triangle, but in a scene, you can have a lot of triangles, right? So there can be a lot of triangles that in 3D, they can be overlapping, and there can be like projected on the same section on your screen, right? So for each pixel, we can have different fragments from different triangles, right? That's why fragments and pixels are different. Fragments are like a 3D projection from the pixel, and they are not unique. That is super important, right? So also something that I usually do is I usually like draw the fragments as circles, right? They're not circles. I mean, they're just data, but it's just like it's the way I used to to create my graphics on my presentations. So every time you see like tiny dots, I'm referring to fragments, right? When you see like tiny squares, those are already pixels, right? But yeah, it's just the way I used to paint them in the presentation. Okay, so the rasterization part, again, it computes which parts of this triangle correspond to which pixels, and also it needs to compute, for example, the color of these fragments, right? So having the information from the geometry processing, so the position of the triangle, the normal of the triangle, the position and the direction of the lights, for example, the rasterization part will compute a single color value for each fragment, right? And then it will pass that information to the pixel processing, and the pixel processing needs to take, for example, several fragments for each pixel, and needs to determine which of those fragments is the real final color of that pixel, right? So, for example, the depth of those fragments is important, right? If you have a triangle that is occluding another triangle, right? We want, of course, to show the color of the triangle that is closer to the camera, right? Because that is occluding the one that is occluded by the camera or occluded by the triangle, right? Okay, so yeah, basically this is like a very simplified version of the rendering pipeline. And something that is also important is that in this stage of geometry processing, okay, in this area of the pipeline is where your vertex shader is, okay? And in the area of rasterization is where the fragment shader is. But this is important. The fragment shader is not the rasterization, okay? So these are not single stages on the rendering pipeline. So these are like areas, right? So if this is a factory, right? We are talking about a factory, it's like I don't know, like rooms, okay? So there's one room called geometry processing and another big room called rasterization, and geometry processing has a lot of stages. One of those is the vertex shader, okay? And one of those, in the case of rasterization, is the fragment shader. And fragment shader and vertex shader are written in GLSL. And GLSL is a specific programming language that is the OpenGL shading language, okay? And I think it's based on C, okay? But yeah, but it's a specific shading language created by this purpose. Okay, good. So this is again a simplified version. Now let's go to the big version, okay? So this is the OpenGL pipeline again, and something that is important to notice is that OpenGL pipeline is a bit different, for example, from the one from DirectX, okay? Because those are different technologies, but they're very similar. Usually, conceptually, they're almost the same. What differs from OpenGL or DirectX, for example, is the hardware architecture, for example. So in different processors, for example, you can like maybe you are computing the same algorithms, but some algorithms are computed in a very specific GPU core in one of the technologies and another different GPU core on another type of technologies, right? And different stages on this pipeline, some of those stages are you're able to program those stages, you're able to control those stages with a GLSL program, and some other stages are totally fixed. For some of those are completely fixed. We will talk a little bit about the math that is involved, and we will do some exercises. So we will see on the lectures, we will see the math of some of those. But many of these sections are close to our control, right? They're totally fixed, and they're processed by hardwired silicon core GPUs on your GPU. Okay, so now let's talk about the first section, the vertex data. This is basically the application stage that we already said, right? This is the one that basically collects everything, all the geometry and scene data, and literally passes everything to the GPU, okay? So yeah, we already said everything about this section in particular. So now let's talk about the vertex shader. This is one of the main areas that you need to know, right? And that is one of the things that you will need to program for your intro assignment and also for the second assignment. Okay, so the vertex shader runs for each vertex in parallel. I think the last time, I don't remember, but I think the last lecture I said that the vertex shader it runs one time per primitive. That is not correct. I made a mistake. Yeah, I didn't mean primitives. I meant vertex. The thing is, the vertex is a primitive, but maybe it was confusing. Maybe, yeah. So, for example, if you're sending triangles, the vertex shader is not computing per triangle, but per vertex of those triangles, okay? And something that is important on the vertex shader is, again, that is parallel, right? So the vertex shader is like a tiny computer inside your GPU, but it's not processing vertex one by one. What happens is that you have thousands of cores inside your GPU, and this vertex shader can be like distributed in these thousands or tens of thousands GPU cores, and it can process vertex in parallel, okay? And because of that, because it's parallel, something that is also super important is that it doesn't know the mesh connectivity. So what do I mean with mesh connectivity? So imagine this bunny here. So this bunny is a polygonal mesh, right? It's formed by triangles, and these triangles have certain connectivity. What I mean with connectivity is that this triangle, for example, has certain number of neighbors, right? This, sorry, you're not seeing my mouse. Okay, so this triangle, for example, here, it has this triangle as neighbor. This is also another neighbor. This is also another neighbor, right? Same happens with vertices, right? So for example, this vertex here has a certain number of neighbors, right? That are connected by these edges. So for example, in mesh processing, in digitally geometry processing, we call the set of all the neighbors of a vertex, we call it an umbrella, okay? So the umbrella of this vertex are these first connections, right? That information is not inside the vertex shader, or it never passes to the vertex shader. And it's important because there are certain type of algorithms in geometry processing that from which we need connectivity information. And the thing is, in vertex shader, you never have in vertex shader, sorry, we never have the connectivity. Okay, so what we were saying, that runs one time per vertex and is in parallel. It has no connectivity information. So as input, it gets the vertex attributes and the vertex coordinates in object coordinate system. So the main goal of the vertex shader is to output the position of each vertex on screen coordinates, and it does that by applying different transformation matrices. Okay, and yeah, we will talk about that, and we will see all those math, right? And it has some output variables. The one that is like the main one is GL position. These are built-in variables inside the vertex shader. This is the one that almost, I mean, you will use every time, and this is the one that is that you can check in any tutorial. But it has more. It has actually 3. So the GL position is basically the final position of each vertex, and again, that is computed by applying different transformation matrices. There's also this one that is the point size. So the point size is information for each vertex that defines, for example, a size for that vertex, and it can also define, for example, different information. I mean, you can. The thing is, imagine that instead of rendering the bunny like this, like a mesh, you only want to render the points of the mesh, right? Like dots. So GL point size, well, in that case, instead of sending information regarding triangles, it will just send a size of the vertex. So in this case, for example, I will need to define inside the vertex shader, I will need to define GL point size depending on its distance to the camera, right? So as you can see here, because I have perspective, right? Points that are nearest to the camera are bigger than points that are farther to the camera, right? So that is computed, that could be computed on the vertex shader, and you can send that information with the GL point size. And the next stages could render this bunny, instead of render as mesh, they can render the bunny as points, for example. But the thing is, GL point size is an optional variable. So if you don't use it, the program will just continue and it will do anything special. If you use it, you need to tell the next sections that you don't want to use triangles, that you want to actually show only dots, right? And this is, for example, very convenient in a certain type of data that's called point clouds. So I don't know if you remember in the introduction to computer graphics, basically our first lecture, I think it was on the extra video, I talk about capture, and I talk about these laser technology that is basically like a laser that is sending it's like a 3D scanner that is basically sending a laser that is moving right around an environment, and every point that is touching that laser in the end is computed as a position in space with its normal, right? So the way you usually visualize the information that you get from 3D scanning, right, is not a mesh, because the information you get is not a mesh. The information you get is just thousands or millions of points on space, right? So that type of data is called point clouds, And the way you visualize point clouds is by using by rendering only the dots, and you can use GL point size to define the position and the color and the size of those dots. Okay, then we have another one that is called clip distance. This is also optional, and it can have the distance from that vertex to a clipping half space defined by the user. I will explain later in deep what is a clipping space, but it basically allows the user to discard that vertex if it's inside or outside of a certain geometry. So sometimes we need to define a certain certain limit to render things. So something that is usual is, for example, limit your rendering to a certain distance. So for example, if you're playing a video game like GTA or something like that, and you have like super huge worlds, right? You usually have an effect of like a fog effect on the rendering, right? That is basically fading the objects that are very far from your point of view. Okay, so if you're playing in a video game that has millions of geometries and like buildings and things like that, right? And there are objects that are super far. What you do usually is you create a fog effect, and there are certain geometries that at a certain distance are already invisible because of this fog. So on that distance, you basically create a plane, right? A far clipping plane that you use to discard every single geometry that is farther from that plane, right? Because I mean, what is the purpose of processing geometry that is not even visible, right? Because it's like very far. So this GL clip distance is one variable that in the vertex shader you can use in further sections of the pipeline to define that a vertex is discarded, right? Okay, so in the end, because the vertex shader, the main purpose of the vertex shader is to define a position on the camera space. The thing is, you can play with that position. You can use different types of variables inside the vertex shader to modify the original position, right? Because in the end, it's like, okay, if I already had the position, for example, in this bunny here, if I already had the position of each vertex in the original OBJ file, why do we need a vertex shader? I mean, what's the purpose other than just applying certain transformation matrices, 4x4 transformation matrices, and in the end create a final position on screen space? Well, the thing is, the cool is that you can play with that position. You can play with certain information that you can send to the vertex shader, and you can deform the mesh. So for example, imagine that we have this bunny, and on the vertex shader you have the position of each vertex, and you can also have the normal of that vertex, of each vertex. If you don't remember what the normal is the normals are vectors that are perpendicular to the surface, right? So it's basically is like the direction that is pointing outside the surface on this bunny, and is basically a line orthogonal to the surface of the bunny, right? So we can, for example, do something like this. You can like inflate the bunny, right? You could take the vertices and take the normal of that vertex and basically move the vertex along its normal. So you could like, yeah, inflate the bunny. Or you can, again, grab some information from some variable that you can send to the vertex shader, and you can define the mesh like a wave animation, right? So here, for example, you can use like a sine wave to modify the position of the vertices, right? So you're not modifying the original model, right? If the original model was an OBJ that you're loading into your code, the OBJ stays the same, right? This geometry is modified in real time in your GPU, just a little bit of like a tiny microseconds before it's actually rendered on your pixels, okay? So this is the most simplified version of a vertex shader. The good thing is that a lot of things that actually the vertex shader does, right? They're done automatically, right? So the vertex shader or fragment shaders, those can be like just a few lines of code, and you can do great things. So for example, this is the minimal vertex shader. This is basically, it's not doing anything. It's just defining the GL position as the original position from the bunny times the model view matrix. So this model view matrix, it's a matrix that it basically contains all the world coordinates and the camera coordinates, basically the view coordinates, and it's just transforming the vertex into a screen position. So it's just a super vertex shader that is basically doing nothing. It's just applying the transformations and passing to the next stage. This is another example. This is the example for example inflating the bunny. So in this case, you could send a uniform variable, and in this case is inflate scale. It's basically the amount of scale that we want. So you could create a new vector, a new vec3 object called new position, in which we are taking the normal, right? And we are multiplying the normal by a scalar, which is this uniform variable that I send to the vertex shader. And this is a vector, right? So we already talked about that. The normals are vectors, and because they are vectors, they are representing a direction. They have a magnitude, which in case of normals are always unitary vectors. I hope you already know what a unitary vector is, because you have some linear algebra knowledge. So normals are unitary vectors that define a position. Sorry, that define a direction, the direction that is orthogonal to the surface of the bunny. And if I multiply the normal times a scalar, I'm just scaling that vector, right? But because it's a vector, I just need to add a new position, right? So basically, I add the original position for the vertex, and this is a new position for the vertex, right? But this is still local, right? So this new position variable contains a new position for each vertex, but this is still on the object coordinate system. So in the end, you need to say, okay, GL position equals to projection matrix times model view matrix times the new position, right? You need to make this matrix composition of transformation matrices to, in the end, getting the GL position in screen coordinates, okay? And again, don't worry too much about this section here right now, because we will talk about a lot of time regarding these transformation matrices, right? So don't worry. Just for now, just think it as some magic 4x4 matrices that will convert from one coordinate system to another coordinate system, to the one that we need. Okay. And there's this question of, okay, so I have these variables called uniform variables. So what are those uniform variables? It sounds like weird, right? So why are they called uniform? So these are the types of variables that you have in the vertex shader. So we have three types of variables. We have the uniform variables, varying variables, which the name is super weird, and the attributes, okay? So uniform variables are like global variables that you send to the vertex shader, but they are global. They are exactly the same for all vertices. So remember, the vertex shader runs one time per vertex, right? So in this case, the uniform variable that I was using on the previous example was this like inflation scale, right? I am using the same inflation scale for all vertices. So for example, if I am moving, let's pretend that I am moving the vertices along its normal in, I don't know, 3 units, okay? Those 3 units are exactly the same for all vertices, okay? So that is one important thing about uniform variables. Those are variables that I am, as a programmer, I send to the vertex shader to do something, to play with my vertices, but those are going to be exactly the same for all vertices. Okay, the variable variables are a bit different. The variable variables are variables that are shared with the fragment shader, or shared with the next stages of the pipeline, okay? So those are computed per vertex. And also something that is very important is that they will be automatically interpolated for fragments. So an example of the varying variable, for example, will be the color of the vertex. So the color of the vertex is an information that I could send to the vertex shader, right? It's computed per vertex, right? But it needs to be interpolated because in the next stages from the vertex shader, the information will be not vertex anymore, but fragments, right? So remember, the fragments are the sections of the triangle that correspond to a specific pixel, okay? And don't worry, I will show you an image of this. So yeah, but for now, let's keep that. So they are automatically interpolated, okay? And again, they're shared, these varying variables, they're shared between the vertex shader and the next stages. Then there are the attributes. So attributes are also user-defined variables that you can send to your GPU, to your vertex shader. The difference between attributes and uniforms is that uniforms are variables that are global, right? They have exactly the same value for all vertices. But the values on attributes, those are values that are actually per vertex. And they're actually at least two built-in attributes that are already on your vertex shader and you don't need to like declare or anything, which is the position and normal, right? And makes sense. I mean, there isn't a single position for all vertex, right? We have one position per vertex and one normal per vertex, right? So these are also user-defined, but these are not global, okay? Also, something that is important is attributes are not shared with the next stages. So attributes are variables that only came to the vertex shader and that's it. They stay there. You cannot recover that information on other stages on the GPU. That is super important because remember the GPUs are usually super powerful because it's the number of cores you have, but passing information between those cores is very critical. So there are certain amount of data that you just can't keep sending to the GPU, right? So attributes, they stay on the vertex shader, you use them, and that's it. They never go further than that. Okay, so this is an example of a varying variable that can be interpolated. For in this case is the color of the vertex. So at the triangle level, the color can be defined as the color of the vertices, right? But at the fragment level, the color needs to be interpolated. So for each fragment, for example, for this, sorry, you're not seeing my cursor. So for this fragment here, for example, the color of this fragment is not exactly the color of any of these three vertices, but a linear interpolation, basically a linear combination between these three colors, right? So that's why you can see like a grading of colors. Same happens with the normals. The normals is also an information that is interpolated from the vertex shader, is interpolated when it's outside the vertex shader to the next stages. So we already said that a normal is the direction that is orthogonal to the surface, right? So usually you compute the normal as the cross product from the triangle, right? So in this case, if you compute the normals per triangle, your render will look like this, right? Because every single fragment, every single section of each triangle that is corresponding to a pixel on my monitor, in the end has exactly the same normal than the rest of the fragments that are inside that triangle, right? Or they belong to that triangle. The way we interpolate that is instead of computing the normals per triangle, we compute normals per vertex. This is basically computing the normals on all the triangles that are neighboring this vertex here, and basically you just average all those normals and you get the normal for each vertex. And then those values are interpolated, right? Using barycentric coordinates, they're interpolated between those vertices, right? So in the end, the render looks like this, right? So you cannot see the quads anymore. You can see that the geometry is the same, right? I mean, if you see the border, it is the same. But in the end, it looks smoother because the normals are interpolated, okay? Okay, perfect. We are on time. Okay, then we already talked about the vertex shader, right? And we are kind of saying that the next stage of the vertex shader is the fragment shader. Well, kind of. The thing is, there are some sections in between. There are other stages in between. So before the vertex shader and sorry, after the vertex shader and before the fragment shader, we have other sections here, and one of those is the tessellation section. Okay, so the tessellation is composed by two sections here on the pipeline, but it's actually composed by three sections. I will explain. So what is tessellation? Tessellation is it's a tiny section in your pipeline that basically decides its purpose is to increase the number of geometric primitives to provide like a better looking models. So this model here, it has certain amount of primitives, right? But maybe if I take a render, like a very close render of these shapes, it will look horrible, right? So one way to improve this is by telling the GPU, okay, don't use the original model, right? But please subdivide the original model, create more geometry of the original model, so the model can look like prettier. Okay, so that is the purpose of this tessellation. This is also called, can call subdivision. Subdivision is an area of study in geometry processing, and there are a lot of algorithms for performing tessellation or subdivision. And again, tessellation is divided into three sections. Is tessellation control shader, tessellation evaluation shader, and a tessellator that is basically in the middle. Okay, so what each section does. The tessellation control shader controls how much tessellation you want. Okay, so you can tell the GPU to say you want one level of tessellation or two levels of tessellation. So basically, if we are talking, for example, about triangles, right? One level of tessellation in one triangle is basically to create 4 new triangles, right? So if you perform a second stage or a second level of tessellation, for each of those new triangles, you will create 4 new triangles, right? So it just increases the number of vertices and it increases the number of triangles. So basically it computes, again, the number of tessellation levels, and it sends a tessellation level to the next stage, which is the tessellator. So the tessellator creates the new triangles based on the level of tessellation that you require. And the last section, it is like a vertex shader. It's basically a tiny vertex shader that computes the new positions and normals and texture coordinates and all the information that is usually computed in the vertex shader, but now you need to recompute everything, but now for these new triangles, right? So again, if I come back to the image, these triangles here, they were not existing on the original model, right? They were not existing. So these are new triangles that are created in the tessellation section. So you need to recompute everything again. You need to recompute the normals and everything, right? So that is the job of the tessellation evaluator shader. And basically what it does is it does computing by interpolating data from the original vertices, right? So it's exactly the same as I mentioned already. The normals are going to be interpolated using the original data with these new triangles, okay? And finally, for today, we have the geometry shader, okay? This section that is, what it does is that it can generate new geometry, right? So the tessellation creates new geometry, right? But based on the actual geometry, just subdivides the mesh. But the geometry shader can just create totally new geometry depending on what you want. So this is a very cool example. So imagine that you have the bunny, and you can tell the geometry shader, for example, to get, depending on the position and the normal of each vertex, it can create geometry. It can create whatever you want, spheres, more triangles, or whatever. So you can, for example, create hair. You can create a hairy bunny, right? And this can be computed in real time, okay, on the GPU with the geometry shader. So yeah, I think that's it. I think we're in a good time for now, taking a tiny break and check if there are some questions. I hope, I'm seeing the chat right now. Yeah, it looks like a cactus, right? I hope you got your questions answered by the TAs, but if not, yeah, so can you show your questions? Okay, someone is saying, bro, so many questions. Okay. Bring the question. Don't even know what I don't know. Okay. Yes, exactly. Please ask me if you have questions. And again, remember that you can ask on Piazza, and I am also trying to answer questions on Piazza, right? Uh, what does the tessellation? Okay, what does the tessellation? The tessellator does. The tessellator is the one that actually creates new triangles, right? So the first stage decides how many new triangles you need. The tessellator creates those triangles, and the final one, that is actually the final one, is the evaluator. The final one takes those new triangles and interpolates, like recomputes its data, its position, its normal, and everything based on the information you send, and also based on the previous data. Does the vertex data include connectivity? Yes, vertex data includes connectivity, but in the end, I mean, you send that data with connectivity, but in the end, when it comes to the vertex shader doesn't know connectivity anymore, right? So basically, the connectivity information is lost between the vertex data and the vertex shader. So what's the stage called? Oh, what's the stage called when you decide? Okay, let me go back, because yeah, the names are very weird. I always forgot. Tessellation control shader is the one that decides how many new triangles. Okay, then it has something in the middle. Sorry, this is a tessellation control shader. Then you have a tessellator in the middle. It's not here, but it has a tessellator in the middle. That is the one that it actually performs the subdivision, right? Create new triangles, and this guy recomputes everything for these new triangles. I mean, don't worry too much right now, because you will not program, you will not code these things. These are also things that are usually automated. You can create shaders for these things. So the modern GPUs, the modern pipeline GPUs architecture allows you to actually control those things. But yeah, I mean, these are super complex algorithms. They have some complex algorithms. Yeah, we will not go like super in deep with this. Vertex shader, everything is points. Tessellator create geometry. Till vertex shader, everything is points. Tessellator creates geometry. Very good question. No, the thing is, a tessellator creates new geometry. Okay, so before tessellator, you already have information as triangles. So basically, the vertex shader outputs information already in the shape of triangles, because remember, at the end, it sends enough information to the next stages to either create new triangles or compute the fragment shaders. The fragments, sorry, not the fragment shaders. I'm confused what vertex data and GL position, the difference. Okay, vertex data is the information that we send to the vertex shader. GL position is the output of the vertex shader. Okay, so the vertex shader, sorry, the vertex data is the input for the vertex shader. GL position is the output from the vertex shader. In a nutshell, what was the geometry shader again? Geometry shader is a tiny stage that basically can create new geometry, but not necessarily based on the original triangles. The difference between the geometry shader and the tessellation, because both sections create new geometry, right? But the difference is that the tessellation subdivides the original geometry. It takes the original triangles and it creates new triangles dividing the original triangles. But the geometry shader can create completely new geometry out of whatever information you send. In this case, for example, like hair or whatever. Does the tessellator add more primitives when it subdivides the original triangle geometries? Yes, of course, because each new triangle is a new primitive, of course. Yeah, triangles are primitives, and yeah, it creates new primitives. What is GL position again? GL position is one of the output variables from the vertex shader. So if I come back a little bit, quickly, the vertex shader has three possible outputs: GL position, GL point size, and GL clip distance. The main one is the GL position. So it's an output from the vertex shader. It's the position of those vertices on the screen space. What's good about dividing triangles? I might not understanding your question. I mean, maybe you're asking like the purpose of that. The purpose of dividing triangles or creating new triangles is usually to create a smoother version of the model. So again, if I go to the example, this model here, it doesn't have much triangles, right? Like many quads. If you get very close to this area, for example, you will see that like the geometry is like very low poly, right? So if you want to show like a smoother surface, you subdivide the surface with the tessellator, and you get just a beautiful, a more pleasant surface. Isn't the position of vertices pass the vertex data? No. No. You're asking, okay, so Doruk is asking if the position of vertices on the screen is passed through vertex data. No. Vertex data sends the position of the vertices in object coordinates. Then inside the vertex shader, you take those positions and you multiply those positions, those vectors, by several concatenated or composed transformation matrices to, in the end, modify those positions and get those positions in the version of screen coordinates. Again, the thing is, those things are maybe a lot like very confusing for you right now, because we haven't covered the transformation matrices, right? You need to understand, guys, that we are seeing learning everything step by step, and there are certain things that I am not I don't need for you to understand at this point, because I know we haven't covered that part yet. Okay, this went from 0 to 100 real quick. Okay, pros and cons animated forwards. Animation model versus animating with shader waving a flag. Oh, very good question, Gabriel. Okay, so I mean, one possible advantage is that if it's an animation done on the GPU, that animation is basically done by equations, right? By math. So you don't need an animator working and moving, right? And moving keyframes to create that animation, right? It's just done by math, and that's it, right? So that is one thing. Another thing is that I'm trying to think. I don't want to say something stupid. Very good question, Gabriel. I will think about it. Because I will give you a lot more advantages. I mean, the main advantage is that animating meshes for a human, as for an animator as human, animating meshes is really, really hard, right? I mean, it's not easy. So just get a GLSL program and write a couple of lines of code with a little bit of equations and have at the end a beautiful animation is way more convenient. But yeah, I will try to search for more advantages. Thanks, Enrique. Thank you, Gabriel. Are we real? Okay. Okay, great. So I think we can wrap right now. If you have more questions, please go to Piazza. Also, if you want to give me feedback about the lectures, they're very welcome. If you think the pace of this lecture was, I don't know, very fast, please also tell me. I mean, this is not an easy course, right? We have a lot of information to cover. Very fast lecture. Okay. Yeah. So that is good. Please tell me that. If you think that it was very fast, tell me. I can maybe modify the pacing next time. Any idea for improvement, please tell me. I love to hear ideas from you, like this thing of putting like suggested readings and everything, right? Enrique, assignment due date. What? What do you mean? But the course web page says. Oh, I'm sorry. I didn't notice. No, it's a typo for sure. If the PDF says, if the PDF has a different date than the web page, the PDF is wrong. I'm so sorry. If that is the case, I made a mistake. Yes, no, the correct date is the one on the web page. Thank you for asking. I will correct that, and I will upload a different PDF. Yes, 25 is correct. And please, like rule of thumb, and I use everything with, I mean, I am human, TAs are humans, we can make a mistake. But for every mistake we made, the resolution will always be on your favor. So don't worry, okay? Let's pretend that in this case, the original due date was 23 and I made the mistake on the web page. In that case, I will keep 25 because yeah, in the end, I need to cover my mistakes, not you. So yeah, but in this case, yeah, the correct is 25. Can we submit handwritten PDF for theory assignment? No, the way you will submit the theory assignment is we will have a quiz with optional optional answers on Canvas, and basically you will need to take your answers and submit it on Canvas. Okay, yeah. The thing is, you need to understand that the amount of people is huge. And decipher handwriting or like checking PDFs will be very hard. So yeah, we will do that. No, for theory you will not use handing. If the webpage says that, or if there was a misinformation, I'm sorry. No, for the theory assignments, you will need to submit your answers on a quiz on Canvas. Yeah, okay, yeah. Thank you guys. Bye.